All right, in this video, I'm going to cover section 2.8, Bayes theorems. So the point is this: as you can see that here, starting from the probability of the intersection of two events A and B. So we uh, learned that this probability can be expressed as in terms of conditional probability, right? So P A bar B times P B, or P B bar A times P of A. So now, so just to get a look at this, P conditional, look at the two sides, I mean, second term and the last terms. So the taking two terms, and then we can express the conditional probability P A bar B in terms of the other conditional probability P B bar A, like this, right? So here, Bayes theorem is this. We wanna find out conditional probability by using other conditional probability. So what if problem just give us a whole bunch of conditional information about conditional probability, and then we want to find out um, a, a certain, a conditional probability. So now then, you may need to use Bayes theorem. So to find out to figure out the deep conditional probability, um, we're gonna use all the information given in problems, and then those informations are actually conditional probabilities. So let's take example. So 2.26. Okay. So yeah, this table we haven't seen this one table in example 2.20. Okay. So that probability of failure is zero point 0.1. That doesn't mean the P of F. Okay, probably not P of F. Okay, that's the conditional probability given that the level of contamination is high. Okay, so actually, see, yeah, this one is that is P of what? If you say the F, but yeah, so F is the failure. Okay, so and then H means the high contamination. Okay, level of contamination is high. Okay, so now then we can say, yeah, so what's F? F is event. What's the event? Event is a subset of the sample space, right? And then event is the set of all the outcomes we are interested in here, the set of all the parts, but parts which are defective. Okay, so now then P of the what F, given that, right, the part is I mean the level of contamination of the part is high. Okay, and then 0.005 is a probability that what a failure. Okay, given that the level of contamination is not high, so H complement of H, right, H prime. Okay, there was a 0.2. 0.2 is a probability of what? Probability that the part is high, the level of contamination is high. Okay, and this is a probability of definitely H prime, right? Okay, so right here. So now look at this. Yeah, so we're gonna use that one, that the equation 2.15. Okay, so now then pH bar F. So we want to find the P of H bar F. It means the conditional probability of high contamination, given that the product is defective. Okay, so failure, I mean. So now then pH bar F is equal to, now then, so applying the that equation 15 into apply this one. Okay, then we're going to get P of F bar H times P of H over P of F. Okay, so now then that is equal to, all right, so P of H bar F, yeah, that's given, right, which is zero point 0.1, and the P of H is zero point 0.2. Okay, what about this? The thing is, how can I find out this P of F? Yeah, so don't say that P of F is equal to P of H F bar H plus P of, I mean, P of F is not equal to sum of two probability. Okay, no. Okay, to figure out this one, we're gonna use total probability. Okay, remember that here, the sample space right there. Okay, the sample space S, capital letter S. Okay, and then here is the F. Okay, so F, and here is the H. Okay, so we can classify the all the outcomes or parts into two groups: high contamination, not high contamination, right? So now then, probability F can be expressed as what? Probability of the what? This is the H intersection F, right? Okay, and then this is H prime intersection F. So remember that, okay? So the probability F is equal to probability of H intersection F plus a union probability plus probability the H prime intersection F. Okay, so now then for each probability of that intersection can be expressed in terms of the what conditional probability, right? So if you don't get it, what I'm saying, please go back to section 2.6 and look at the independent total probability and then its example. Okay. So now back to yeah. So here my lecture note here. So applying the total probability into P of F. So we got this. You see that P of F can be expressed as like this. How come? I told you because we use the total probability. Okay, the formula. So we got this. Now P what? We know that the conditional probability F bar H, which is 0.1, right? This is 0.1, and then F bar H prime, that's 0.005. And the P of H is 0.2, P of H prime is what? 0.8. So now then we can figure out P of H bar F. Okay, so normally the problems they asking you to find the P of H bar F, but the problem give you this is unknown and what you have to find out, and the problem give you the information about conditional probability F bar H. Okay, probability of F bar H is given, but the problem asks you to the opposite of conditional probability, which is H bar F. Then you know normally you have to use Bayes theorems with the total probability formula. Okay, keep in mind this. Now it's back to the yeah, textbook here, and then yeah, this is the Bayes theorem. Okay, so E1, E2, E1 through EK are mutually exclusive, and exhaustive events, and B is any event. Yes, and then yeah, so here, give me a second. Let's see. All right, sorry about that. All right, so here, let's say this is sample space here, and then let me draw the E1 through EK. They are events. They are mutually exclusive. So say here E1, say this is E2 and E3 through the what EK right there. Okay, and then set B is right here, like this maybe. Okay, this is B. Okay, and this is E1, right? Through the this is E2. Okay. So now you understand that, right? So then probability that conditional probability of E1 bar B can be expressed as probability B conditional probability of B bar E1 times P of E1. Okay, that's the what? Probability of B what? Top one represent what? This is a probability that what? B intersection E1, right? Okay, right. So which is this? Okay. That one represent probability that the part belong to the what outcome belong to this uh that set. Okay, and then the bottom one is yeah, this is probability of B intersection E1, and then this is what second term represent what probability that what B intersection E2, right? Okay, So you need to completely understand the what the relationship between the conditional probability and the probability of the intersection. Okay, so otherwise it's hard to understand these understanding what I'm saying. So what last one is what this is equal to probability of what B intersection. Oops, it's B intersection EK. EK. This is EK. Okay, EK right here, which is the this part right here. Okay, so mm, now look at the example two. Before doing this, so when you look at my lecture, give me a second. So I just simplified that formula-based theorems. So as you can see that here, the bottom one can be expressed as it's as the sigma summation. You know this, right? Conditional probability of B bar EI times P of EI, and the I goes 1 through the K. Okay, so we can express this. Now let's see example 2.27. So example 2.27, yeah, because a new medical procedure has been shown to be effective in the early detection of illness, and the medical screening of the population is proposed. So the probability that the test correctly identifies someone with the illness as positive, known as sensitivity, is 0.99. Okay. So now, and the probability that the test correctly identifies someone without illness as negative, okay, is known as the specificity, okay, is 0.95. The instance of the illness in the general population is 0.0001. That you take the test and the result is positive. What is the probability that you have illness? So, all right, let's see. Here in this problem, example 2.27. So, yeah, first I draw the Venn diagram right there, and then let's say a capital letter D denote the event that you have the illness. Okay, and then capital letter S denote the event that the test signal positive. Yeah, so normally the capital letter S used to denote the sample space, but this example, I'll I use a capital letter S, okay, because yeah, the problems use the that letter. So, okay, so the given information is the problem says that the test correctly identifies someone with the illness as positive. That means the prob is 0.99. It means the probability that the test result positive, given that who the guy is just has the illness. Okay, so that's condition probability, right? 0.99. And then the problem says that the instance of the illness in the general population is 0.0001. So it means that the probability of the ill that someone has illness is 0.0001. Now, and then the problem says that the probability that the test correctly identifies someone without the illness as negative, it means the probability that as prime, right? Because probability that the someone got negative test result, given that actually the guy has no doesn't have illness, right? So the 0.95. So interesting is this. You can make a table like this. Okay. So uh, so we have four cases. So okay, do you have illness? Yes or no? Okay. So if a guy has a illness, let's say for example, again, a guy has an illness, and then had test result positive. That's the probability S bar D, right? Okay. So now then, and then right. So and then the 0.99 right here. Okay. And then the what if the guy got negative test result? It's called the first negative. Okay. So the test the guy got test result and then negative, but actually the guy has the illness. It's called first negative, and then that's the probability. And then probability. This one is called the can be expressed as conditional probability, like this probability that S prime bar D. And then But if the guy doesn't have illness and then but got positive test result, the first positive probability S bar D prime, right? And then the other one is S prime D prime. Okay, so problem give us actually three information. Two of them is this 0.99 P of S bar D and the P of S prime bar D prime. Okay, so now the interesting is this. You know what? Actually, P of S bar D prime plus P of S prime bar D prime must be equal to 1. And then P of S bar D plus P of S prime bar D must be equal to 1. So the 0.99 plus this guy must be equal to 1. So first negative, probability that guy got first negative, that should be 0.01. Okay? And then since this is 0.95, the problem says that, which is given. So this guy must be what? 0.05. Okay, how come? Because the other interpretation of conditional probability is what? Reduce the sample space. Okay, what that means, we're talking when you calculate probability, we use what? Classical probability. Remember that probability of, for example, probability of, oh, not here. Give me a second. So yeah, so think about this probability of for example, yeah, S is what? Actually, number of the outcome in sample space divided by number of, let me use the other thing. Let me say D, okay, D, sorry. So probability of D is equal to number of outcomes in the event D divided by number of outcomes in sample space, right? Okay, but now the probability of S bar D, when you calculate this one using the classical probability, then this is going to be number of outcomes in a what outcomes in S intersection D over number of outcomes in the event D. Okay, so sample space is going to be, I mean, the denominator, I mean, definitely numerator is changed, right? But also denominator is also changed, which means that we can say the sample space is just reduced by D when you calculate the conditional probability. In that sense, here, take a look at this. Look at this conditional probability the S bar D prime and then S prime D prime. So here, S prime D prime is actually what? S prime, to calculate that conditional probability, S prime bar D prime, we're gonna figure out number of outcomes in S prime right here, right? S prime right here, divided by number of outcomes, what? D prime. Okay, you see. So S prime is what? Where is S prime? S prime right here. Okay. This is the S prime intersection D prime. I'm sorry. Okay. So that's the S prime intersection D prime, right? Okay. And then what's the D prime? D prime is this. Oop. Okay. That's the D prime, right? Okay. So then what's what about the S, you see, conditional probability S bar D prime? Then, so we have to calculate number of outcomes in what? S intersection D prime, which is here. So that's the, can you see that right there? Okay, can you see that? So this is the S intersection D prime. Okay, S intersection D prime, right? Divided by number of outcomes in D prime, right? Okay. So then what? So simply saying that what? The probability that, so these two probability has the same denominator, right? Number of outcomes in D prime, right? And the number of outcomes in S intersection D prime plus number of outcomes S prime intersection D prime is nothing but what? Number of outcomes d prime, right? Because d prime can be expressed as what? S intersection d prime, which is that part colored by yellow, plus what? S prime intersection d prime, right? So since the d prime is equal to what? S intersection d prime, right? Union, right? And then S prime intersection d prime. You see? So it means that what? Implies that probability of what? The d prime can be expressed as what? Probability that what? Let me see. Not probability. Ooh, no, no, no. Actually, S. Oh yeah. Not here. Oops. I already mentioned right here. So probability S bar d prime plus S probability S prime d prime bar d prime must be equal to 1. Okay. Let's see. So now because this guy is equal to what? Probability of S intersection d prime divided by probability d prime, and then this guy is equal to what? Probability of S prime intersection d prime over probability of d prime. Adding that, excuse me, adding them up is nothing but what? That means what? This one, by the way, S intersection d prime, S prime intersection d prime are mutually exclusive. There is no common outcomes. So what? The probability P of d prime is equal to what? P of this guy plus P of that guy. Adding them, these two guys is equal to what? This one plus that numerator, which is equal to what? P of d prime over P of d prime, which is 1. So this one problem says that S prime, P of S prime bar d prime equals 0.95. That must be 0.05. Okay. Now then, okay, back to here. So question is this. The problem question is to find the probability that a conditional probability d bar s. Why? Because the problem says that you take test and the result is positive. Okay, so that's the assumption. Okay, that's a given. And then what's the probability that you have the illness? So we can say that what's the probability that you have illness given that you got positive test result? Okay, so now we're going to use a Bayes theorem. By the Bayes theorem, this we can express that conditional probability as like this. Okay, so P of S bar D is given, which is 0.99 right here, and then P of D, the problem says that what 0.0001, and then P of S bar D is 0.99. This one P of D 0.0001. Now this one P of S bar D prime, which is what first positive, right? What was this? 0.05. Why? Because this is given, which is 0.95, and then that one plus that probability plus this probability must be equal to 1. That's what I explained it like here. Okay, so this is 0.05. So this is 0.05 times 0.00. P of d prime is what? P of d is a 0.0001. It means that P of d prime is what? 1 minus 0.0001. Okay. Okay, so there's only two answer, right? Do you have illness? Yes or no, right? So P of d prime must be what? Complement of P of d. Okay, so plug those numbers into here, in there. So we got this, which is 0.002. Okay, so the if you you need to understand all this stuff. Okay, completely. Okay, so that's the Bayes theorems. Okay, now let's see 2.9 random variable quickly. Okay, so what's the random variable? So random variable actually is a function. Okay, a mapping from the sample, the outcome in sample space to the real number. Okay, so that's the key mind. So random variable is a function. This key mind is okay. So the once we do experiment and then we got some outcomes, and then through the random variable we're gonna the convert all the outcomes to the random here to the real number. Here's the example. So okay, the when you just think about this, just simple experiments, rolling a die. Okay, this is rolling a die that we expect a 1, 2, 3, 4, 5, 6, right? And then let's say I'm interested in even number. Okay, so we construct the event. Let's say A, event A is set of all the outcomes whose number is even number. Okay, so then we can expect, okay, so then 2, 4, 6, right? Okay, so now then this simple here, okay, even number. All right, so now then the we're gonna just rolling a die, then for example 3 times. Okay, just 3 times. So now then we're gonna then we are interested in the number of odd numbers. Okay, interested. So we got the, maybe we got just 0 even number, or a 1 even number, 2 even number, or 3 even numbers, right? Okay, so now you see it's 0, 1, 2, 3. That's the range of the random variable. What's the domain? Is an event. All the outcomes are event. Okay, so keep in mind this. So here's a now see notation. The random variable is noted by the uppercase letter such as x. After an experiment is conducted, and the measured value of the random variable is noted by a lowercase letter such as x equals 70 milliamperes. So lowercase x is just represent specific value, okay, of random variable, and the capital letter x used to just as used as a variable, kind of, okay, random as a variable. Now, there are two type of the random variable. You can see that discrete and the continuous. Discrete is a finite or countably infinite. Okay, so for example, is the natural number. Okay, 1, 2, 3, 4, 5 is countable, right? Even though this is infinite, we can count. The continuous is, for example, integer, or just real numbers. Okay. So see examples of random variable. Example of a continuous random variable is the electrical circuit, electrical, current and length and pressure, temperature, time, voltage, and the weight. Discrete is number of scratches on the surfaces, and then proportion of defective parts among 1,000 tested, and the number of transmitted bit received in error, and stuff like this. Okay. So now we move to the chapter 3 next time. Chapter 3, we're gonna see specific probability function. Now we deal with the function, but that function represents probability, okay, of certain sample space. So we'll see that section, chapter 3 next time. Okay, let me stop here.